My name is Dmitry, and I want just to share some raw thoughts about computer data networks, discovery, and composability, and how Fluence can help. What's our approach on this topic? So I decided to go straight from the fundamentals. I will speak about data, computer data, network. What does it mean to have a computer data network, and why do we need many? What does it mean discoverability, composability? What does it mean computer data networks, discovery and composability? And finally, when we have some understanding of the problem, I will tell what we at Fluence do to help with this problem. So first of all, data and compute. Data is things known or assumed as facts, making the basis of reasoning or calculation. And to compute, from my opinion, it means to shuffle data in a certain way for a purpose. So data is usually needed in a different form that it appears. It appears in some raw form, but it's needed in another. And what does it mean another form? It means aggregated, reshaped, analyzed, filtered, augmented, indexed, searched, and so on. So we need data in many shapes and forms. And compute actually accompanies data all the way, and the same holds for data. So if we want to capture the fact, it actually means that we can yield this fact without providing something before it. It means that we have some way represented as an arrow here to get some data as letter A. If we transform data, it means that we provide data, we have arrow, some compute to have another data. If we have an intermediary state that is held between different invocations of compute, then we have this kind of arrow, like state monad, that we have some internal state and input, and provide the new kind of the state and output. And this state change, it may help with augmenting data, it may mean storing data and providing nothing as the result, and so on. And finally, to finalize the life cycle of the data, we need to consume it, for example, to show it, and we have some kind of sinks for the data. And it means that you provide the data as an argument, and you have nothing inside the system out of it, but you have some effect, for example, something shown on the display. So there's no way to compute without data. Compute without data makes no sense, absolutely no sense. You cannot see anything. If compute without data makes sense, it means that there is data involved actually. It was consumed or exported or something happened. And data without compute is the lost fact. It happened, but it even isn't stored, so it's just lost. So some more arrows and letters. We have some predefined compute, and providing the data and getting CID is also a compute job. And it's not always trivial to compute CID, and it's not always easy to understand that this file represents this CID and not something else. And sometimes we offload this compute, even this compute from the client to the server, for example, if we stream data, or if the data is too big and we just upload it, and then we get back CID. We have this arrow inversed, and that's not quite compute. If we get from CID to data, it means much more than compute, because we need to discover it. And a lot more things involved here. And we can think about the user-defined compute, which is an arrow without data yet, but ready to get it. And luckily, we can represent it as data as well, like WebAssembly binary or Docker, or like any code finally is data. So compute over data by definition, from my point of view, implies that you can get an arrow C and place it where the data is, so that finally you compute over data. And place it where the data is means either to move compute closer to the data or to get data closer to compute. And both cases make sense, I'm not sure that we can limit all the use cases just to one, like batch processing, or to another, like runtime, real-time processing. Both cases make sense, and fundamentally, it makes sense because it's just more efficient. The closer the compute to data, probably the more efficient the computation is. And it brings more privacy, more security, and overall it's fine. Then a few words about the network. It's a concept which is orthogonal to compute and data. And I wish we could just skip it. If we could not think about the network, things would be much, much, much easier. But in the real world, physical world, there is such big latency and bandwidth distinction of physical resources that we are forced to treat these resources as somewhat independent peers. So we just have to, it's physics. But if these resources have something important in common, if they share some attribute, then we can organize a network out of them. So this network is identified by this attribute basically. For example, if we know that some peers are storing a data set, or we want to put this role on these peers, like say, these peers, please do store it. We want to identify it as a kind of a network so that they can help each other, or maybe they can help us to work with this data. Or if we have some special peers with specific compute capabilities, GPU access peer is very different to laptop, for example. And maybe we want to organize them in networks as well. Or particular things served for a particular user. For example, if I made some kind of a deal with some service provider, then these peers, despite the fact that there are better peers for like physical resources, but these peers are ready to serve me because I have financial relationships with them, for example. So all of this matters and means that we have a lot of networks. We have place to have a lot of networks, which kind of could be very big as protocols, but they also could be very small. For example, all the providers of a particular file for a given CID on the IPFS network, effectively, they also form a kind of a network by this attribute. And basically, network means shared connectivity and or agreements over data within a set of peers. So either you can find the root over the network, and that means that it is a network. For example, if you can get a peer by peer ID by Katemlia, it's mainly about shared connectivity. Or we have some agreement over data, like consensus. All the different kinds of consensuses, including eventual, weak consensus, like strong consensus, any type. It's about agreement over data that all the peers will probably share or be capable to yield some particular data that like conforms to some invariants. Now let's speak about compute over data networks, also with arrows and ladders. If we think about IPFS as a network as a whole, then every IPFS deployment constitutes a compute over data network. And compute here at least is getting CID or getting from CID to files. And the notation could be something like we can yield a function from CID to maybe data. If it exists, if we can find it, maybe data. We can think about every IPFS node as a single peer cache network or any subset of these nodes as a cache network, so that we provide a peer ID and have this function that works with a very different like latency, because we look up locally and use IPFS as a hot hash instead of using the network for content discovery. It's very different. For compute, we should have many compute over data networks for different geography. For example, if we wanted them locally, or for types of compute, or for different ways to compose this compute. But fundamentally, it means that somehow we can have an access to the peers that can take our compute in some form of abstract arrow, like WebAssembly, for example, or Docker, or whatever. And after that, we will have an ability to execute these computations on data. So the notation becomes longer and longer. And also we can think that a single device, even one device, or like a small set of user devices that belongs to one user, for example, they also constitute a single device computer data network that, for example, provides the way to capture facts from, I don't know, measurements or click streams or something like that. So we can think about all these kinds of devices and workloads as different kinds of computer data networks. Then comes discovery. So discovery means that we need to yield some capabilities out of thin air. So previously we had this, from nothing we get some capability, and that's discovery. And we have a lot of different domains that we want to discover for and in. For example, for different types of data sources, we want to discover data sources, be it devices, access to the chain, access to sensors, to external events, to randomness. It's different data sources, but we need to find a way to get this data. Or for a type of data store, cold storage, like Filecoin, hot storage, blockchain as a storage, whatever. Or a particular data set, we need to find this particular data set. Or a kind of compute capacity, we need GPU, we need whatever, we need ZK kind of compute so that we need certain proofs. And does this compute fit for a certain data that we want to provide? Is it possible to connect data source to compute capacity? Do we need to prepare the data before we do compute? And for efficiency of everything above, we need to employ very different discovery algorithms. So there must be some solution on top of that to think about all these problems in some layer that just simplifies them, or at least lets us speak about it, like to have the common language to speak about all these problems while they seem different. And in Web 2, we have solution. So when we just do Web 2, we have a lot of easy ways. The most easy ways is to point on the local capabilities, like local host, file system, local CPU, or something that you have in the web browser. Just call function in JavaScript or write a variable. That's the access to data and to compute. Very simple. Or for the remote capabilities, usually just have a REST endpoint, something XYZ, like some host in Fura, I don't know, that gets to DNS for discovery. And we have this discovery layer hidden in a fundamentally centralized way. But if we get to the endpoint that fulfills our needs, we're just happy. So absolutely good. Web 2 is very optimized for that. And we may discover computer data networks the same way with the gateways. And many people are happy doing just in Fura or something like that. So let's switch to composability. what to compose, and why. What we want is to utilize the same network or sub-network, it could be a small network, or the same compute capabilities or the same data wherever they are as building blocks for something more complex to deliver the value to the end user. One example is data processing pipelines. So you have some device, something that produces the facts that we want to capture and analyze. It could be really a device like the phone, but it could be the chain, the access to chain. It could be the source of time, of randomness, other triggers. Then we have the edge, like relaying node in libp2p, for example, or the closest cache, or we could like do some filtering, pre-processing, and it means that we want to do it very close to the device just for optimization, because we might get an insight very fast, or we can filter out unnecessary data very fast, or we can do a small aggregate and prevent the further processing until we collected some data. So it's efficient. After that, we could have some real-time processing close to the edge. Probably we want to have the same region. We want to have good latency to get some real-time insights or to store some data in the read models, to have some databases for like application level. And finally, we store it into probably Filecoin to the cloud. We accumulate a lot of data. We batch process it because we have a lot of data available, and this is a very different domain. So the question is, if you want this, how to express this pipeline? What is the way to speak this pipeline, to approach this pipeline? How to code it? Especially given that we have a lot of discovery processes here and different protocols, because probably edge nodes is a sub-network that is capable for doing one thing, while cloud is a very different set of peers and different hardware, different capabilities, different connectivity, different latency. So, and where should this data pipeline be expressed? Given that, for example, we have just these 4 levels. Who owns this pipeline from one level to another? Who writes this code? Who deploys it? And where to deploy it? Is there any place to deploy it? Who, on the way, we have the user data, probably. We get some insights, we make some decisions, we should transfer some permissions. So a lot of questions about security that were like ignored or exploited in Web2 world, but we want to do better. So for compute over data networks, discovery and composability, if we take all the words together, so what we want is to utilize many networks with different kinds of resources and attributes. We want to point to these resources and have the single flow of processing. We want to take resources by geography latency, by different ways to establish security, something ZK, some consensus, some trust, different kind of access to data. It could be real-time, hold, cold chain, whatever. We have different compute capabilities, and we want to point on them. We have a very limited amount of peers actually connected to the end user, to the device, and that's the question, is it connected or not? Can we only pull data, or can we also push notifications and so on? And we want to have a single pipeline. And in this case, we will have this computer data as a big product composed of different protocols. So, coordinator to organize, to orchestrate this workflow seems very inefficient. Because if we think about just these 4 layers, there could be much more there could be less, but if you think about just 4 layers, then there is no good dedicated place or location, and even geographical location or protocol-wise location. What network should it be like located in, or should it be a Web2 like endpoint? Just no very efficient place. In Web2, it's not the case, because you can have everything in one place, and you can you can have one endpoint that actually leads to the workflow being executed inside like the cloud. But in Web3, probably not. And also, if you have a coordinator, it's going to be too powerful in terms of ability to censor the facts, or to change them, or to move them to some other storage that user haven't authorized to work with this data, and so on. All of this could be managed inside a single network. So if we say that compute over data is actually about creating just one network that is a one-stop shop that does everything, probably it would be enough to have some protocol inside this network to discover the right place to have the call and so on. But in the real life, even for Web2, one network is not enough. And even in Web2, we have different solutions for the edge, and different regions, and different stores, and so on. So probably what we want to have is finally a flow of service composition that is coordinator-free, permissionless, like ready to be composed and integrated with different protocols. And we want to have this workflow to look somewhat like this. So we have certain steps, and we can describe the workflow, be it some kind of controller for a user interface, or really data processing, or anything like that. We can abstract it out to something that consists of very simple steps. For example, I want to get data, then I want to discover the edge peers which are ready to serve me. Like, ideally they should be prepared. Then I run compute on the edge. I wait for the proper results, given the consensus or security capabilities of these edge peers and proofs. After that, I discover some kind of fog, some intermediary computations for the real time. I move the control flow here, run compute on fog, wait for proper results and proof, and after that, I discover storage. Like, why should I discover? Because it could depend on the data that I got from the fog compute. For example, I could determine the right shard which points on the subnetwork, on small network, only during this computation. I cannot, probably, I cannot have everything in place from the very beginning. But I can discover every next step, and after this, like, discover, run, wait, discover, run, wait, discover, run, wait, and finally done. But if these peers are not prepared to serve me, if they're not warmed up, then I want to have the pipeline like this. I try to discover edge. If I cannot, I'm trying to do latency-based discovery to find the closest peers, deploy the code on them, so that to prepare the edge nodes. The same for the fog. I want to find the capable peers. If they are not ready, if they are not in cache, deploy the content on them. So on every step, I do some computations. I have the decision about the next step, and I push my requirements to have the next step prepared for me. So until everything is done. And when it's done, it doesn't mean that it's just stored. I might want to have the proofs that everything was done, that everything is okay. Or maybe I want to distribute some incentives or to have some acknowledges. So ideally, the pipeline should look like this, and it should not depend on any particular network. So that's about the Fluence approach. Given all of this in mind, we created a set of tools that makes it possible like today. So first of all, we have an Aqua. Aqua is the way to express these workflows, which are like decomposed into this discovery compute steps with maybe some provisioning, like deploy something or not, or failover or not, and so on. You can compose distributed workflows which are suitable for open networks from these basic steps. It's push-based, so next peers are resolved on the fly, and you can take the actual real-time connectivity into account so that you can optimize the way. You don't say want, you say I'm going here because it's meaningful for me. And a push-based approach means that still having an open network, you involve the minimal amount of peers possible. And the minimal amount of peers means that it depends heavily on the discovery mechanics. If you have log n, then you have log n peers. If you have several logarithmic discovery processes, like in Kademlia, then you have k log n or something like that. But if you can reduce the scope of lookup, so for example, using not the whole Kademlia or the whole network, pretending that all the peers are the same, but instead if you can, using some attribute, select a subset of the big network and organize some kind of Kademlia on top of this, then it's much more performant. And if you have a hot cache, it's even better. So, but fundamentally, it depends on how exactly you write the code, and you have full control. It works on top of libp2p, but it doesn't require you to recompile, rebuild, redeploy the network or the networks. So if some protocol is ready to serve Aqua, then it's just ready, and you can use it for composition without any additional communication with the team, I don't know, protocol forking and so on. And you can have different workflows. So it's open for integration with all the other protocols. And as the result of execution, as the side effect, it provides an audit log that only what you expected to happen have happened. And you can use this log, and we're going to use this log for the incentives layer. With Aqua, you can express these smaller networks on top of compute over data network protocols. So subnetwork is a network formed around a certain resource or attribute. For example, data for a user or peers of protocol N close to region G. It's an attribute or a set of attributes, or peers capable to access some data like blockchain B, which run Fluence, and at the same time which run, I don't know, Filecoin, for example, so that you can access the new blocks. And with Aqua, you can do subnetwork formation using Aqua just libraries to interconnect, sync, bring code on peers, deploy provision, and so on, because all these network concepts of having connectivity or having agreement over data, they could be also decomposed to single workflows. And if you can have a set of workflows to run on the network without the end user interaction, with these workflows, but instead with the subnetwork, then effectively you have the subnetwork. You can have subnetwork discovery as an Aqua library as well. And the composition of subnetworks, which means pushing data and control flow to the next and next and next subnetworks, meaning peers of these subnetworks, because nothing magical. It's just a new line character. You get from one line of the code to another, and it could mean moving compute and data to the next peer. And finally, Aqua is part of Fluence, and you can think about Fluence as the workflow stack for compute over data network discovery and composability. Yeah, CoD, ND, and C. So Fluence accompanies protocols to help them organize push-based and purpose-driven workflows. So we are open for different protocols as a sidecar or as libp2p protocol. With Aqua, the language, you can describe the workflow, orchestrate, provision, and so on. We have Marine. Marine is a WebAssembly runtime to run compute, or probably highly likely to lift another API or protocol running on the same peer to Aqua. So just to enable the composition, you can write a very small WebAssembly to use the capabilities that you already developed in another protocol. Or if you don't want to do it, if you want to do all Fluence with all the portability and so on, you can do pure WASM. And Fluence as network is a libp2p based network for Aqua and Marine to enable a discovery and composition of all the parts. There is a huge amount of missing details in my talk, so I was just sharing our thoughts and approach. And if you want to learn more, take a look on fluence.dev, or let's chat after this and after the break or during the break. I see that everything is prepared. So thank you for your attention.
Hi, thank you for the talk. I have 3 questions, but maybe, I don't know, can start. Have you thought about load balancing on peers? So you said your pipeline is discovery and then push computations, right?
I haven't touched this aspect, but let's think about load balancing as a data-driven discovery algorithm. So what does it mean? Load balancing means that you have a network, a set of peers, and these peers can do some job. And they are, maybe that's one of the approaches, they are at least aware about each other, and maybe they're aware about each other's current load. So this is the shared data, and then the discovery algorithm that takes this data into account is just a part of the workflow. So we've been developing these things as well. We have some data about the workload provided by default as the part of the protocol, so you can do this as well.
Okay, thank you. Yeah, because I mean you cannot push every computation to the same peer if the same peer is doing all the computations, right?
Yeah.
Okay, so the second question, which I thought, so you talked about doing discovery over Kademlia, correct? Or some Kademlia with some property on top, right?
Yeah, I said the word Kademlia, and I said that for some cases it would be nice to have Kademlia built out of the workflows, to have small Kademlias, because using big Kademlia sometimes it's an overkill.
Exactly.
So actually you can decompose Kademlia into workflows, and you have many Kademlias on the same set of peers serving different purposes for different service location. But it's not the only way to locate services.
Exactly.
It's just one of the ways.
My question is more like, so a DHT is good for an exact match kind of search, right? And here it seems to me that you want to do any match search. You want to find any peer that has this property, correct?
Depends on the use case. Sometimes I do, sometimes don't, but I'm not limited with the CoD. We are in progress of developing attribute-driven CoD. But that means that you have attributes. If you have something more complex, like a set of filters to find the proper peers, probably you need some data index to help you to decompose this set of properties into a set of discovery rules. This part is being in R&D. We can discuss it. It's very funny. We have some Bloom filters and so on, but not sure that it's the only way to solve this problem. So, yeah, this
I would be
is the
interested in discussing this with you.
Thank you. Hello, thanks for the talk. I've got a question about a use case where you don't know how many nodes you want to send work to before you started computing. So maybe you run the workflow and get big data and you're like, okay, I want to send that to 100 nodes and shard it out. Or maybe you get small data and you think, actually, I only need 2 nodes for that. Does Aqua support that sort of thing where you don't understand the shape of the execution up front and you work it out as you go along?
Well, you need to understand the shape because otherwise it's super unsecure to serve this workflow because we care about the security of the peers who participate in this workflow. But Aqua is based fundamentally on PyCalculus, and in PyCalculus you have this, like, I forgot the word, the fixed point analogy, recursion, kind of recursion. So basically, in Aqua you can do the for loop, and you can do for loop for parallel branches, which means that you can get the data, for example, the list of subscribers, and then you can do in parallel based on data, many threads. And we are trying to solve the problem of amplification attack. In this case, we have some solutions, but it's an interesting topic. And basically, yes, Aqua allows to do it, but you need to have the code that expresses the workflow before you send it to the network. You need to sign it, otherwise there is no way to deal with amplification attack during the runtime.
That's cool, thank you.
Thank you.
Hello. Do you have idea of market or payments built in your reasoning?
Of what? Sorry?
Market.
Payments. Yes. We are in the process of finalizing the deal marketplace, which is akin to what we have in Filecoin. And for the entity that the payments will be distributed to, we have a subnetwork. So if you have a resource, you have subnetwork for this resource to have fault tolerance and something like that, and to have a capability for peer rotation. And you have a deal with this subnetwork to serve some job with you. And then I said that we have audit logs as a side effect of executing the workflow. And this audit log contains kind of the proofs of some peers serving jobs for a particular subnetwork. And eventually, with a golden ticket-like mechanics, we send this proof to a Rust-enabled blockchain to find the subnetworks and to distribute the rewards. This is the, like, in short, our approach to economy. We can talk about it more during the break.